we propose TensoIR, a novel inverse rendering approach based on tensor factorization and neural fields. Given multi-view 2D images captured under unknown lighting conditions, our NeRF-based method can reconstruct BRDF, geometry, and environmental lighting of the target object, supporting applications such as relighting. Such a task is often called inverse rendering reconstruction. Unlike previous NeRF-based methods that use purely MLP-based neural fields, thus suffering from low capacity and high computation costs, we extend TensoRF, an efficient radiance field modeling approach, to perform inverse rendering. Benefiting from this representation and our special designs, our method can model secondary shading effects more accurately, have higher quality and faster speed, and support input images captured under single or multiple unknown lighting conditions. We can do the inverse rendering reconstruction by adding more components to the architecture of the original TensoRF and designing a novel physical-based rendering pipeline. Let's first look at some results before talking about more details. Here is the reconstruction result from one of the synthetic data LEGO. When compared to the NeRF-based baseline, NeRFactor, and the SDF-based baseline, InVRender, our method demonstrates significantly improved geometry reconstruction quality. This is the albedo reconstruction comparison. This is the novel view synthesis comparison with physically based rendering. Once we have reconstructed the BRDF and geometry of the target objects, we can utilize these parameters for relighting under unseen lighting conditions and material editing. Here are some results from captured real data. More results can be found on the paper and the project page. Now, let's delve into a more detailed discussion of our method. Following the TensoRF VM decomposition, we decompose high-dimensional tensors into a set of matrices and vectors. The density can be obtained through simple interpolation. The surface normal, BRDF and radiance color can be acquired by passing the features into three separate small MLPs. During training, for each 3D point along a camera ray, our model will predict its radiance color, volume rendering density, BRDF, and surface normal. Then, we will use the classic volume rendering formula to compute the radiance field color and the radiance color loss for the corresponding pixel. We will also compute the surface depth to get the surface point position. After that, we will compute the physically based rendering color on that surface point and get the physically based rendering color loss. The process of computing the physically based rendering equation requires getting the incoming lighting that a surface point receives from various directions. It is important to model them efficiently and accurately for an inverse rendering reconstruction task. For direct lighting, our method represents it with 128 spherical Gaussian lobes. During training, we will generate 512 light incident directions with stratified sampling by randomly generating one incident direction inside each grid of the environment map. Then we will query light RGB from spherical Gaussians with those incident directions. Regarding visibility, which can be used to model shadow, since our density field is represented as an explicit grid, density can be calculated by interpolation without the need for any network. This allows us to compute visibility by sampling points along the incoming light direction, calculating density, and performing online integration, without the need for pre-trained networks like the visibility network used in previous methods. For the indirect lighting, we query the color value of the neural radiance field at the sampling points along those incident lighting directions from the previous step and use it as indirect lighting, avoiding the expensive computation of multi-bounces of ray tracing. Compared with previous NeRF-based methods such as NeRFactor that rely on a pre-trained visibility network, our method can get more accurate visibility modeling with less noise. Therefore, we can generate realistic and accurate shadows when relighting. Here is a visualization of our indirect lighting modeling during training. Since the geometry of the density field in NeRF is not well defined and contains a lot of noise, we predict the surface normals using a small MLP. The normals predicted by this normal net are used in the computation of the rendering equation and are also constrained by the derived normals obtained from taking the derivative of the density field. The normal net is supervised by both the observed images and the derived normals, receiving information from two sources. Normals prediction will also affect the geometry, which can help us improve the quality of the underlying density field. Our method also supports inverse rendering reconstruction of images captured under multiple unknown lighting conditions. These images captured under multiple light sources correspond to different radiance fields, and we need to reconstruct these radiance fields to compute visibility and indirect lighting. At the same time, the density of these radiance fields can be shared. And the surface normals in BRDF are consistent across different lighting. We extend the original 4D feature tensor of TensoIR into a 5D tensor, with the additional dimension corresponding to different lighting conditions, while sharing the same 3D density tensor. Our decomposition is extremely efficient, with the 5D tensor only adding a few vectors compared to the 4D tensor, resulting in less than 1% increase in storage overhead. The radiance colors are predicted from radiance features that vary across different lighting. The materials and surface normal are predicted from intrinsic features that are consistent across different lighting. Here are our rendering reconstruction results for multi-lighting data. Here are the corresponding geometry and material reconstructions results. Here are our environmental map reconstruction results under a multi-light setting. Different lighting corresponds to different maps. Multi-light settings can also help improve the geometry and material reconstruction quality. Different from previous methods, NeRFactor, InVRender, and REF, which divided the reconstruction process into several stages to pre-train, distill, and so on. We optimize all components together in a single stage, allowing them to mutually enhance each other. Thanks for listening.